In this video here, we're going to take a look at modeling with graphs. So we're now going to discover how graphs and networks can be used to create mathematical models. And in decision maths, the word graph has a very specific meaning, and it is important that you do understand the difference. So a graph consists of points, often just called vertices or nodes, but for consistency, I will just stick with vertices here, but if you do prefer nodes, that's absolutely fine, which are connected by lines, often just called edges or arcs. And again, consistency here, I will stick with edges, but if you do prefer arcs, again, that's absolutely fine. And if a graph has a number associated with each edge, usually known as the weight, then the graph is known as a weighted graph or network. So for example, this here is a graph because it consists of points, often just called vertices or nodes. So like I said, I just prefer to call these vertices. So I've got A here, B, C, D, E, and F, right? And as we can see then, they're connected by lines. So for example, this is AF here, this is AB, BD, BC, you get the idea, right? So let me just make a note here then that this is a weighted network. So weighted network. Okay. So in terms of an introduction here, right, to modeling with graphs, we don't need much more than that. Obviously, within the next couple of videos, we will go into more detail and discover the special types of graphs that you do need to be familiar with. But for now, this here is absolutely fine. So let's just work through a quick practice question together. So let's just have a go then at the one practice question for this video. So what we've got here then is a network below. It shows the time in minutes taken by a car to travel along different sections of road. And again, we can see that here on our network. Now for this question then, all we want to do here is calculate the minimum time required to travel from A to D. So that's from this point here, this vertex to this point here at this vertex here. And we also need to state the route taken. Now let's just be slightly careful then, because what we've got here is a weighted network, right? Now, a weighted network is not usually drawn to scale. So what might appear to be the shortest or the quickest route here might not actually be the shortest or quickest route. So what we need to do then is consider the weight of each arc, okay? So to do that then, what I'm going to do here is just right at the top then, potential routes that we could take. So the routes that we could possibly take then to get from A to D, and also the time needed then in minutes to get from A to D by following that respective route, okay? So we've got the route here, like so. What we've also got here is the time needed in minutes. So time needed, and again, this will be in minutes. Okay. So I'm going to present this almost in the form of a table. Do make yours a little bit neater than mine. I'm doing it freehand without a ruler. Obviously, just use a ruler, right? It doesn't have to be as messy as mine. Anyway, I digress. So what routes could we take here to get from A to D? So I think the most obvious one here is from A to B, B to C, and then finally C to D, right? So the route there is A, B, C, D, right? And in terms of the time needed then, that would be 9 plus 5 plus 3. So 9 plus 5 plus 3. What does that give us here? 14, 17. So it takes then 17 minutes by following this route here. So let's just keep going then. And basically all we want to do here is just exhaust all the possible routes then, okay? So if I just extend this down a little bit here, like so, what other routes could we take here to get from A to D? So I think another obvious choice here is to go from A to E and then from E to D, right? So the route there is A, E, D, like so. And in terms of the time needed, then that would be 6 plus 10. So 6 plus 10, and in that case, then it will take 16 minutes by following this route here. What other routes could we take here? So we could also go from A to B, B to E, and then E to D, right? So I've got A, B, E, D there, okay? So for the time needed, then that would be, so it's going to be 9 plus 5 plus 10. So 9 plus 5 plus 10. What does it give me here? That's 14 plus 10, 24 minutes there. Okay, so clearly we wouldn't choose this route here, but we're just going to exhaust all the options, right? Just to show clearly which route we're going to take here. And then finally, just one more route here. I could also go from A to E, E to B, B to C, and then finally C to D, right? So A to E, E to B, B to C, and then finally C to D. So for the time needed, then that would be 6 plus 5 plus 5 again plus 3 there. So what is that? 16, 19 there. So 90 minutes by following that route there. And at this point here, we've now exhausted all the possible routes. Any other routes that we would kind of, choose here, we'd basically be going back on ourselves, which clearly is not going to give a minimum time here. So that's absolutely fine. So at this point here, then, we can now identify the minimum time required to travel from A to D, and we can also state the route taken. So to finish with them, let me just make a note here. So the minimum time required is, so what would that be then? So that would be 60 minutes here, right? This is the shortest time. It's going to be 60 minutes. And that would be along the route, and that's this route here, AED. So along the route AED. Okay. And there we have it then. So hopefully you find this example here quite nice and straightforward. And there we have it then. So that gives us our solution here to the one practice question for this video. And that just brings us to the end then of this video here on modeling with graphs.